Here's part two of column and footing design. We're going to go through an example now. Here's a simple two-story building. You can see that we're working on this column right here. Notice it has a roof load to it, and also it has a second floor loading to it. So it says size of spread footing for column B3 in the building shown below. The footing thickness is 1 foot 9 inches. Assume that the footings bear on silty sand with an allowable soil bearing pressure of 3,000 pounds per square foot. Again, here's our three-dimensional view of the relationship between beams, girders, and the columns. So what's not shown on this is we would have a roof that's being supported by these columns as well. So this is that second floor. First floor would be down here. And again, what's not shown is that we would have some roof girders and roof beams supporting the roof. Here's straight down. You've seen this before. We have girders acting on the beams, acting on the columns. We have two beams that are acting on the columns as well. So what we're trying to do is we're trying to figure out the loading on this column right here. So it says, assume the engineers perform the analysis for the floor and roof members with the following results. So roof beam reactions are 5,000 pounds each. So this is the end reaction. The girder reaction is 10,000 pounds. So that's for each one of the beams and each one of the girders. And then for the second floor, we have reactions of 13,500 and 27,000 pounds. So here's a vertical picture of the column. We have a roof, we have our second floor, remembering that that first floor will not be included in the column loading. So from the roof, we have our two end reactions, 5,000 pounds each for each one of the beams of 10,000 pounds. We're also going to have two girders that are acting on that column as well. So 2 times the end reaction of 10,000 gives us 20,000 pounds. From the second floor, we have two beams acting on it. Each are 13,500 to give us 27,000. And we have two girders acting on the column as well. And each of those are 27,000 pounds times 2 gives us 54,000 pounds. The one other thing that is included in this is the actual column itself. And so now notice that this says 1,500 pounds. What's not included in this, or the assumption that is made, is we don't know how much it weighs per foot, and we don't know how tall it is. Very often, what we can do is we can make the assumption that the column weight itself is 50 pounds per 1 foot. And so if that's the case, then we could say that this column itself is 30 feet tall times that 50 pounds gives us 1,500 pounds of load for that actual column itself. So now what we're going to do is we're going to add up all of these loads to get a total column load of 112,500 pounds. So that's the loading that's happening right here at the bottom of that column. The other thing we have to do is we have to calculate the net allowable soil bearing pressure. So remember back in the problem statement, they were talking about that this is going to be placed on silty sand. It has a soil bearing pressure of 3,000 pounds per square foot. However, what we also know is that we have a foundation that is 1 foot 9 inches thick. So what we need to do is we need to take away that weight from our allowable soil bearing pressure. So we know that the load of the footing is the thickness of the footing times 150 pounds per cubic foot. That's the density of concrete. So the loading of the footing is 1.75 feet, 1 foot 9 inches, times that 150 pounds per cubic foot gives us 262.5 pounds per square foot of that footing. In this equation, I know I'm going to subtract my allowable soil bearing pressure, or subtract the footing from the allowable soil bearing pressure. So I have 3,000 pounds per square foot. That's based on that silty sand. This is my number from the load of the footing. Therefore, my Q net, or my allowable soil bearing pressure, is 2,737.5 pounds per square foot. We're going to remember that for a little bit. So here's that area equation. Area of the footing must be greater than or equal to the load of the column divided by the allowable soil bearing pressure. So when I do that, I have 112,500 pounds divided by my allowable bearing pressure of 2,737.5 pounds per square foot. When I do that, I find out that my area must be at least 41.1 square feet. So what we can do with that information now is we can size what a square footing would be like. Now this, if I want to try and figure out the square footage or the side length of a square, could be very simple. I could just say, I'll go skip through that one. The area of the square is side length squared. Here is my total area equals x squared. X is the square root of 41.1. And I get some goofy number like 6.4 feet. Well, what I can do is I can round up. And so in this case, we just rounded up to 6.5 feet by 6.5 feet by that prescribed 1 foot 9 inches thick. So that is the chunk of concrete that needs to be poured underneath a column to support that load. If I were to do a round footing size, very similar, I could say the area of the circle is pi r squared. This is the area I need to get to. When I go through the math, I find out that I have a radius of 3.6 feet. So with that, what we're doing is we're just again rounding up to say I can use a 7 foot 6 inch diameter round footing by that 1 foot 9 inches thick. So hopefully this helps to where now we can calculate the column loading. We can also calculate the footing size.